Terraform can run commands on servers. Ansible can provision them. Give both the same job, and your next infrastructure change becomes a guessing game. And if you've ever had to debug an infrastructure pipeline at 3 in the morning, you know that a guessing game is the absolute last thing you want to be playing with your production state. So which tool should own what? Well, we aren't here to just read off a generic feature checklist, and this certainly isn't some sort of product fight to declare a generic winner. The reality of modern infrastructure is way more nuanced than a simple comparison matrix. What we actually need is an objective, pragmatic look into lifecycle ownership inside a real evolving cloud service. Because frankly, that's where the architectural theory hits the road, and where poorly defined boundaries will absolutely burn you. When you let both tools fight over the exact same tasks, capability overlap quickly turns right into an ownership collision. You end up with unpredictable race conditions, broken state files, and deployments that just fail for seemingly no reason at all. But if we look closely at how these systems are actually architected to behave, a clean default usually emerges. Terraform builds the long-lived cloud objects, like your network, load balancers, and compute hosts. Then, an explicit handoff lets Ansible configure the packages, files, and services running inside them. Let's trace exactly how this cause-and-effect relationship works in practice. We begin our story with an empty cloud account. It's a super standard scenario, right? A team needs to build a repeatable network, establish a secure boundary, deploy a load balancer, and spin up a set of compute hosts. It's a completely blank slate. And a blank slate is honestly the perfect, and sometimes the only place to establish strict, unforgiving boundaries before the technical debt starts creeping in. Terraform usually owns these initial infrastructure objects, and for good reason. Its configuration naturally forms a strict dependency graph, meaning it ensures the network actually exists before a host tries to attach to it. More importantly, its state gracefully binds those local code addresses directly to the remote cloud objects. What's absolutely crucial here is the planning phase. Terraform's plan explicitly compares your configuration and state against the refreshed remote infrastructure before applying a single thing. This creates a highly reviewable, predictable lifecycle for any additions, changes, or replacements you're making to those core components. The resources now exist, but they are not yet a working service. Think about it. Those cloud objects are happily running in your provider's data center, drawing down your budget, but they completely lack the operating system packages, the internal routing, and the application configurations actually needed to serve traffic and deliver any real value. This is exactly where the explicit handoff occurs. See, Ansible needs an inventory to know what to connect to. It receives an explicit target set, usually through a dynamic inventory plugin or a platform integration that actively reads the new tags and IP addresses generated by Terraform. And it is critical to note here that raw Terraform output JSON is just data. It is not automatically a valid Ansible inventory file. You have to have a proper transformation or plugin sitting in the middle to translate that raw state into actionable targets. Once that target data is securely handed over, Ansible takes control. It uses its agentless connections and ordered playbook tasks to make host and service configuration practical. Instead of just tossing brittle bash scripts at a wall and hoping they execute in sequence, state-aware modules step in. They systematically ensure a required package is present, render the intended service configuration templates, dynamically notify a handler only when appropriate, like maybe restarting a daemon, and finally, ensure the application service is enabled and started on boot. Now, a core concept we have to view conditionally here is idempotency. A second playbook run with the same inputs against a stable target should usually report no change because most built-in modules are specifically designed to avoid making changes when the desired state already exists. But we have to be pragmatic about this. Not every arbitrary shell command or complex playbook guarantees this behavior. Idempotency is a feature of a thoughtfully written module. It's not some magic guarantee of the platform itself. Overlap proves capability, but capability does not settle ownership. The apparent boundary between these automation platforms is incredibly useful, but it certainly isn't absolute in the real world. Both tools have really expanded their reach over the years. So let's take a skeptical, objective look at where their features actually cross over. To be completely honest about their capabilities, Ansible has a robust AWS collection module that can easily create and manage EC2 instances, VPCs, and load balancers all on its own. Conversely, Terraform can run post-apply provisioners, like remote exec, to upload files or execute inline scripts on a newly spun-up host. But HashiCorp actually advises exhausting purpose-built alternatives first. Why? Because Terraform cannot predictably model provisioner behavior in its state file, and managing direct SSH or WinRM credentials inside Terraform just adds entirely unnecessary security complexity to your infrastructure layer. So let's look at how this plays out during a day 2 reality check.
Things inevitably break, or they get changed outside the pipeline when someone starts to panic. Imagine a manual drift scenario. An operator, maybe trying to put out a fire, edits a security group directly in the cloud provider's web console. Because the security group belongs strictly to Terraform's managed infrastructure lifecycle, detecting this rogue edit is super straightforward. A simple Terraform refresh and plan workflow predictably exposes that manual difference between your code and reality. The plan then proposes a highly specific correction action to safely overwrite the console change and return the cloud object to your declared version-controlled configuration. Now consider a second manual drift scenario. Let's say an engineer SSHs into a host in the middle of the night and manually edits an Nginx service configuration file to troubleshoot an ongoing issue. They fix the problem, but they leave the drift behind on the local disk. This internal file setting belongs to Ansible's desired configuration. The template difference is exposed, and the intended content is seamlessly restored the next time the relevant playbook runs against that host. But we must be really clear about a technical limitation here. Ansible does not continuously monitor hosts on its own, nor does it keep a Terraform-styled persistent state file tracking that Nginx config. It relies entirely on subsequent automation runs to enforce that intended state. Clear ownership turns drift into a routing question instead of a tool fight. By establishing exactly which system manages the cloud boundary and which system manages the ingest files, your team knows exactly how to respond and which specific pipeline to run when things inevitably drift in production. There is zero ambiguity about who owns the fix. If you're enjoying this deep dive, consider liking this explainer and subscribing to DevOps Corner for more DevOps and infrastructure content. Replacing that host exposes what the handoff must carry. You know, configuring a brand new, stable host on day one is one thing, but completely destroying and replacing a node weeks later, that puts our architectural contract to the ultimate test. When Terraform's lifecycle rules dictate that an infrastructure object must be removed and recreated, maybe due to an AMI update or an instance type change, the handoff process becomes absolutely critical. The new output, tags, or dynamic inventory source must fully update Ansible's target set with the replacement node's identity before any configuration can safely occur. If you skip this explicit handoff and just fire off a playbook run, you risk executing against orphaned IP addresses, taking down the wrong service, or completely missing the new host entirely. When you need to make intentional day 2 configuration changes, Ansible's check mode does provide a helpful preview of what will happen. It is a simulation mechanism that previews supported task behavior and exposes file differences before you commit. But remember our skepticism of absolutes earlier? Check mode is just a simulation. It should never be equated to Terraform's exact state plan because unsupported modules might simply report nothing, and dynamic target conditions can behave quite differently during a real execution compared to a dry run. And this brings us to the standard default boundary that serves as a highly reliable baseline for most environments. Terraform usually owns the long-lived cloud, network, and platform objects. Ansible usually owns the ingest packages, files, running services, and application deployment orchestration. Now sure, a very small team, an immutable image design, or a heavily managed service architecture might shift or shrink this line. But as a pragmatic starting point, this default represents a remarkably stable design for separating your concerns. So the crucial point we arrive at isn't some empty slogan about declaring a generic tool winner. The ultimate reusable rule you can take back to your team is this. Establish one lifecycle owner per object or setting. Define an explicit handoff contract between your tools and allow absolutely no duplicated control over the same resources. Once Terraform confidently owns your infrastructure layer, the immediate next risk your team faces is state corruption from concurrent operations. We will be covering exactly how to safely manage that in our next explainer, titled Terraform State Locking: How Teams Corrupt Infrastructure. If you found this helpful, make sure to like this explainer and subscribe to DevOps Corner for more deep dives like this.